Greetings and welcome to part 2 of episode 6 in Radio Design 401, where we are talking about low noise amplifiers and how to do noise analysis. The issue is that in addition to noise coming into our antenna and competing with our signal for our ability to receive the signal, noise is introduced by circuits in our receiver. And in part 1, we focused mainly on the effect of that on real-world systems. But here, in part 2, we're going to focus more on the actual circuits, where the noise comes from, but primarily on how to analyze the circuit and design the circuit so that we can get a good low-noise amplifier. So here's the circuit that we introduced in episode 1. It's a common base low-noise amplifier. And this is also covered extensively in the Radio Design 101 series. Today, we're going to talk about analyzing it, but we're also going to talk about how to simulate this and use the simulator to help us, and then how to measure noise figure. And just for fun, at the end of the section on measurements, I'm going to propose a little homemade noise source that you could build a lot cheaper, like $60, than a commercial one, if you want to do some of these kind of measurements. All right, let's get going. This is our outline. And in part 1, we covered these first two things. I'll review a tiny bit of that because any good class needs to begin with the stuff that you did before to remind everybody. But we're going to then dive into how to do the analysis. So to review, there are a couple of equivalent definitions of noise figure. At the receiver system level, this equation down here at the bottom implicitly defines noise figure. And we said that it basically is the amount by which the sensitivity of the receiver is degraded. And this is all in decibels. So if you have a 3 dB noise figure, then your sensitivity of your receiver is going to be degraded by 3 dB. But then we focused on the more traditional definition of noise figure, which is given in this equation. The signal to noise at the input divided by the signal to noise at the output. And this could be for the whole front end, or as we'll do today, it could be just for the low noise amplifier itself. This we mapped into this other form, which is the total output noise from, say, the LNA divided by, for example, the gain of the LNA times the thermal input noise. And the output noise is always bigger than the denominator, which means that the noise factor is always greater than 1, and noise figure is just 10 log of that, and so that means it's always greater than 0 dB. Something like 1 dB is really, really good. Something like 3, 4, 5 dB is usually okay for most receivers. So to analyze an LNA circuit, like this example, we need to know basic circuit design. And again, I'll refer you to Radio Design 101 series. We also need noise models for the components. So we need to know how to model the noise produced in resistances like that one and that one and that one and so forth. And in reactive elements, although we said last time that these reactive elements are approximately noiseless if the quality factor of them is large. But the resistors are decidedly not noiseless, and we came up with these equations. You could do a Thevenin type of model with the resistance in series with a random noise source. Or, if it's more convenient in circuit analysis, we could consider the Norton equivalent of that. And here is the noise current. And a special case is the antenna itself, which, if it's resonant, it has a resistive impedance, a resistive source impedance. And so we've drawn the model over here. This is the antenna source voltage from the received signal power. And this is that source resistance. But now we have the noise source in here as well. And it has the same formula as we had for a simple resistor. And finally, in our amplifier, we usually have a transistor somewhere, or more than one transistor, and we went over this model for that last time. Now, I didn't talk about FET transistors. They have a slightly different model with some different equations, but you can look those up online if you need to. All the basic theory that we're going to cover today is the same. Doesn't matter if you're designing CMOS circuits or circuits with bipolar junction transistors. So let's get on with the analysis, and then we'll go to simulation stuff and measurements. Here is the analysis procedure. It's a lot like the circuit design procedure that you would use for coming up with this, with some special twists down here. The analysis of this circuit, as you know, if you're in electronics, involves first solving the DC bias circuit, and then solving the AC circuit, which provides us our gain and so forth. So we're doing this. The DC gets us our transconductance value for the transistor, and then from that, AC analysis can allow us to find the voltage gain, for example, from Vn to Vc at the center frequency, which is determined by the LC network. And then in noise analysis, we replace this Thevenin equivalent with this one that includes the noise source. And we use the voltage gain that we found with basic circuit analysis to find the expected noise at the output over here from this noise in this source resistance. And I'm going to call that V noise ideal. It's ideal in the sense that it would be the case if the circuit itself did not introduce any excess noise. But we know that each of these elements, with the possible exception of the reactive ones, they introduce some noise that will show up at the output as well. And to find that, we have to replace, say, R3 with its noise model in either the Thevenin form or the Norton form, whatever is most convenient, and then solve for how much noise voltage is produced over here just from that element. So when you look at this resistor here and we're doing the noise analysis, just imagine there's a noise voltage. I'll put it down here at the bottom so it looks more like a Thevenin equivalent circuit working from ground on up. And so it injects noise into here, it gets amplified and shows up at the output. And what step 3 says is we do that for R3, then we do it for R1, etc., until we find all of the individual contributions to the noise at the output. And then finally, we add those all up. But you don't add them like superposition. You don't just add the voltages. You have to add them on a so-called power basis, which we'll look at in the next slide, but I want to just not skip over the last step. The last step is, now that we know the voltage from all of the noisy components, and we also know the voltage that came from the source resistance, the ideal output noise, we take the total of all of that and divide it by the ideal, take 20 log, that's 20 log because now we're in voltage domain. We take 20 log of that, and that is our noise figure. All right, let's see how we add these things on a power basis. So the noise sources are random. So they're not sine waves, they're random waveforms, and the more bandwidth you have involved, the more noise you get. I should mention that as part of the review, so let me review that slide real quick. A lot of times, in fact, perhaps most times, people use what's called normalized noise. So remember, the noise in the resistor was 4 kT R sub S B for this antenna, but B we take as a 1 hertz bandwidth. And then we have this new formula that doesn't have B in it, so that it's universal. We can use it in any case, but the units are weird. It's voltage per root hertz. I'll let you puzzle over that if you want, but let's get back to it. So all of these noise sources are random. They are generally uncorrelated with each other, and that means that you can't add them using normal superposition. Instead, what happens is the noise powers basically add. And so to get the total noise voltage, we have to use this formula. Why the squareds? Because, you know, power is voltage squared divided by resistance. So it ends up being this. And you take the square root of that and you get the total noise at the output. Okay, so buckle up because we're going to do that now. We'll use this example circuit, which is basically the one I just showed you. It has a little bit of extra here with a couple of inductors instead of just one resonating with a parallel capacitor. But otherwise, it's basically the same circuit. This was done to get the resistance seen by the currents leaving the collector lower than it would be without using the split inductor here. That just gives me better dynamic range, but that's not our subject today. Our subject today is noise. So let's launch into this. First step, solve the DC and AC circuits to get the transconductance and the voltage gain at the center frequency. I'm going to assume that you're either kind of working in this field or you have some inkling of how to do that. And if you want, you could review the lectures in Radio Design 101 series. But let's go ahead, take a look at this circuit. First, I'll orient us. This is the source over here on the left, obviously. And this was our matching network. We come into a common base amplifier, so the base is AC grounded with C7. And the output signal comes out on the collector, and then it goes to another matching network, which is kind of merged in with the LC tank circuit. Let me show that. So here's that output matching network, but we've absorbed the inductance in the output matching network, combined it with the inductor in the LC tuned circuit. So we don't see the inductor explicitly here, but it's in here. All right, but first thing we have to do is solve the DC circuit. So let's talk about that. This circuit runs on a 3.3 volt power supply, and it looks like it's biased with R9 and R8 at the base. So what do? We use the voltage divider formula to find the voltage at the base. And if I recall, that ended up being 1.8 volts DC. I've written it as 1.75 because there's some base current DC coming in here. And so that's going to drop this voltage a little bit. These numbers are not exact. If you calculate this, you will not get exactly 1.75. I'm not an exact person when I'm designing these circuits because there's so many simplifications that take place. We'll use the simulator later to refine our estimates, but this is a close one. So 1.75 DC at the base. How do we get the emitter voltage? We drop the base emitter voltage, the so-called on voltage of the transistor, from 1.75 down to 1 in this case, because if you look up this transistor, you'll find out that at the current that it's running, it's about 0.75 volts, not the proverbial 0.7 volt drop from base to emitter. Anyway, so we get about 1 volt at the emitter, and then 1 volt divided by 200 ohms is 5 milliamps. Why did we do all of that? Well, because we need to get the transconductance and then the voltage gain at the center frequency. Okay, so let's jump over to the bottom right-hand corner of this diagram. And it says the transconductance is, well, the formula is IC, the collector bias current, divided by NVT. For this particular transistor, N is not the 1 that you see in most textbooks. It's actually 1.5, so that's where that came from. That's the junction grading coefficient. It's not ideal in this particular device because it's not an abrupt transition from N at the emitter to P at the base. This is the collector current. We just solved for it. It was 5 milliamps. And then VT is what? KT over Q, and that works out to be 25 millivolts or thereabouts. So you crunch this, and you end up with 130 milliamps per volt for GM. Now, to get the voltage gain, first thing you have to do is figure out what voltage gain you're talking about. So I explicitly defined it as the collector voltage AC divided by the emitter voltage AC. This is the input at the emitter and the output at the collector. And we know from Radio Design 101 that for a common base amp, it is GM times RC, the resistance the collector sees looking out. And, oh, that's pretty complicated here. Going back to Radio Design 101, we know that for a parallel LC resonant circuit, we have to have the quality factor. And if we have that, we can figure out what the net equivalent parallel resistance of this is. There's some losses in it, which here is captured in a loss resistor R2. So that models both any losses in the capacitor, which is usually pretty small, and the quality factor of the inductance. which for the inductors that I used in this circuit ended up being close to 100. So that's where the 0.6 came from. In any case, if you know the reactance of either the inductor, which is the net series here, or the capacitor, here it's 62.8 ohms, 63 ohms. If you know that and you multiply it by the Q, then you get the effective parallel resistance from this node here to this node, which is AC ground. And that works out to be about 6,000 ohms. This split inductor circuit was covered in one lecture of Radio Design 101, and what happens is, because these two are equal, you get about a quarter of that 6K here, or about 1,500 ohms. So 1,500 ohms to ground from the LC tuned circuit. But oh wait, look, there's a load over here, and there's the matching network. And when I converted the 50 ohms at the load to what it would be looking in here, that was another 1,500-ish ohms. So you'd have about half of that seen by the collector, or 750. I changed that to 700 because there's always some extra losses from, say, C8, and this is not exact anyway. So I just changed it to 700. Now, back to our story. What's the voltage gain? The voltage gain from Vn to Vc is equal to Gm times R. Gm is 0.13, R is about 700, and so that's about 91. That's a lot. That's a lot of voltage gain, but that's just from the emitter to the collector. That's not from the very input of the amp to the output. Now, it could have been even more had I not done this split inductor thing. Remember, from this node to ground is 6K, and so it could have been like 4 times that. And that would be way too much, because what would happen then is, even for like a 5 or 10 millivolt signal here at the emitter, we would go out of the active region on large signal swings on the collector. So that's why I reduced that. But again, that's just from the emitter to the collector. So what is it for the entire amplifier? From the input, which is here, not here. This is the source. If we have a matched input, then this is 1/2 of the source. That's why the AC voltage is given here as 2. So that when I probe the output, the voltage I get will be the gain. But as the signal goes from the source into the amp, through the amp, and then to the output, we get a gain of 91 from here to here, but coming in, there's a gain in the matching network of about 0.4, because we're matching from 50 ohms down to 1/130 milliamps per volt. That works out to be 0.4 for the voltage gain in L3C5 matching network. Again, see Radio Design 101 for where that comes from, the lecture on matching network design. Likewise, on the output, when we go from 1,500 ohms down to 50, not 700. 700 is the net of what you see looking this way and what is presented by this stuff. Anyway, you go from 1,500 down to 50, that's a voltage gain of 0.25. And I just punched my calculator again. I think it's closer to 0.2, but anyway, this will work. So what do we do to find the total voltage gain from the input of the amp, which is here, to the load, or the output? Well, we take the cascaded gains. So 0.4 here, 91 from here to here, and then 0.25, or 0.2, I use 0.25, and I got 9. So that's the gain from the input to the load. Oh my, we're still on step 2. We're not going to spend forever on this slide. I'm going to speed up here in a minute. But all right, so that's 9 for the voltage gain. And so that is applied to the voltage from the source, which I say is 0.45 nanovolts. So where'd that come from? Well, remember, in the noise model for the antenna, we have an extra voltage source here, like this. And if you use this formula, it works out to be 0.9 nanovolts per square root hertz, but that is the unloaded voltage. So we'd have a little noise source here, which is 0.9 nanovolts per square root hertz, but then we're driving into a matched load. So standing here and looking to the right, we have 50 ohms, we have a voltage divider, so we have half of that. That's where the 0.45 nanovolts per square root hertz came from. Anyway, the bottom line is that the noise, in the ideal case, when nobody else is contributing noise, just the source, is somewhere around 4 nanovolts per square root hertz at the final output. So now we can use a simulator. I'm using LT-Spice. There are many others that can do this analysis, but I'm using that to do the, no, I'm never going to use a simulator to do the analysis. We need to do the analysis so we understand the circuit and what things we want to change to optimize performance. However, what simulators are great at is checking our result and also looking at things that are too complicated for us to throw into the analysis ourselves. We keep the analysis approximate, but we use a simulator to check. So let's see what the simulator thinks those voltages are. The red curve here is the final output noise voltage, total. The blue curve is the noise that was contributed by this source right here. So after you've run the simulation, a noise analysis simulation, in LT-Spice, you can hover over any component you want, and you get this cute little probe symbol pops up, so you know that you're about to probe it, and then you click on it, and it will tell you what the contribution to the total is from that particular one. Now this is the antenna source impedance contribution, and it gives us this blue curve. And we calculated 4, this thing says it's 3.6. So hey, that's pretty close. So I'm kind of satisfied with that for analysis purposes. But we're not done. What we need to do next is solve for the gains from each component to the output. And I'm just going to do a couple of these, and I'll start with the really easy ones. So let's say we want to find the contribution from R8. So here's R8. Now the noise model would have a voltage source in series with it. So imagine it's down here. And so you have a voltage source from ground up to that. You go through R8, and then what happens? Oh, look, C7 shorts this out in an AC mode. So you've got massive low-pass filtering going on here. So there isn't any noise voltage to speak of at the base. So we don't have to do any calculation. And that's great, because doing these calculations is a pain in the butt. With R9, it's the same thing, because C7, again, is bypassing the base with a low impedance to ground. So the bias network's not contributing anything. We said that these reactive elements, if they're decently built, won't contribute anything either, so we're not going to talk about those. We need to talk about R1 and Q1. And perhaps R2 up here. Although I'll just skip to the chase and tell you that R2 is such a small resistance that the noise voltage introduced at the output is negligible compared with that contributed from R1 and Q1 especially. Now what about R1? Again, there's a voltage source, a noise source here, and R1 looks like it, oh look, it's loaded by whatever resistance we see looking into the emitter, which for a common base amp is 1 over GM, and GM is this, so that's 7.7 ohms. And we have a matching network over here that converted 50 ohms at this node down to another 7.7. So what's half of 7.7? It's about 3.6 or something, right? So we got about 3.6 ohms to ground here, and we got 200 ohms here, so that's a massive voltage divider. So whatever noise voltage is here is really not going to be causing us much problem. And we'll see that in the simulation later. It is mainly Q1 that causes the issues. So let's look back at the noise model for the transistor. It looks like this in simplified form. The normal AC model has R pi, it has GMVBE in it, and it has the little RO. It is this INC, which perhaps I should have called I sub NCE, because this noise current is from the collector to the emitter. In any case, the value is given by this. And if you think through it, this turns out to be on the order of the noise that's coming from the input of the amplifier, because it's coming from a source resistance after the matching network that looks like 1 over GM. And so this current right here, it's actually a little bit bigger than it would be from a source resistance, which would be this. So the noise current in this transistor from collector to emitter is going to be a dominant factor in the total output noise. That's the conclusion from all of that. So let's find out how big that's going to be. And more generally, let's find out if some of the simplifications and the things that I said were not contributing noise at the output are true. In our analysis, I said that it looked like we had about a gain of 9 from the input here to the final output. The simulator says 7.9, which is a little less, but still in the ballpark. So I'm not upset with my analysis. It's not like I made a big mistake. I think the voltage gain in the output matching network was the issue. I had 0.25 and later I found out it was 0.2. So that would account for this. Anyway, here's the simulator analysis. And where did it come from? Well, I ran a so-called AC analysis in a linear sweep with 1,009 points from 88 megahertz to 108 megahertz. And the result is shown over here. Here's 88 megahertz, here's 108. We're peaking at about, what is that, 98 or 99 megahertz. And the peak is about 18 dB. So since this is a voltage gain, we have to take that out of dB using the voltage formula. And so it's 10 to the 18 dB over 20. And that works out to be 7.9. Now, what's this blue curve? That is at this node here, Vs sub n, says that right here. And I did that to make sure that this node was 50 ohms looking in. That would mean that our 2 volts would go down to 1 volt here, and that would be 0 dB. And sure enough, at the peak, come down here, we've got 0 dB. So it looks like this thing is well matched. That's just a confirmation. Oh, and I had the marker on the peak, and here are the actual numbers. So it is 98 megahertz, 98.367, which is 98.4 to any reasonable degree of precision. And I could just call it 98 megahertz. And the Y value is 18.071, which we could call 18.1 dB, or just, it's 18 dB. And I know I may sound like I'm being sloppy, but I have built enough circuits over the years to know that there are still many simplifications that aren't even captured in the simulation here. There is, for example, inductance in this capacitor, or more precisely in the layout that runs from the ground to the base of the transistor. So this is not really AC grounded, and that's going to throw off numbers quite a bit. So this could be an error by 1 or 2 dB even when you build it. So what that graph has just shown us is the voltage gain at the center frequency. Now we need to find out the expected ideal output voltage if the amplifier was noiseless. And then ultimately what it is with all the noise sources involved, and then finally the actual noise figure. And here is that simulation. So I modified the command to the simulator from running in AC mode. I commented that out with the semicolon and introduced this one, which is a .noise command. And you have to tell it what output node you're looking for. This is a reference node. I'm not even sure what that's used for. I'm not using it here. And then again, the sweep parameters are the same. So when I did that, I found out that the total output noise here, VO noise, is basically 6 nanovolts per square root hertz, to be precise. Now we have to compare that and use that against the ideal output noise if the thing was noiseless. This 6 came from the simulator running the analysis from every component's noise source to the output, and then adding them up using the sum of the squares and the square root of that. So the simulator did all that for us, and it got 6. But we need to know what the ideal is. In the noiseless case, we know that there's 0.45 nanovolts per square root hertz here coming in if this thing is matched to 50 ohms, which we showed it was. And so we take that and multiply by the gain, which was 7.9, and we get 3.6 nanovolts per square root hertz. So that's what you would have here instead of 6 if nothing in the amplifier was contributing noise. So the noise figure is 20 log of 6 over 3.6, which is 4.5 dB. Now, some simulators will do this calculation for you. They'll have a noise figure command, and you can just ask for it. But I had to calculate it manually here. As far as I know, I don't know how to make LT Spice do that for me. But I don't need to know because I know what I'm doing here. We walked through how this all works. And so this is the final calculation. And that's a respectable noise figure. Remember I said 1 is really, really good, and 3 to 5 or so is okay, and well, that's okay. So, good amp. But let's take a look at what are the major contributors and check our comments where we said that R8 doesn't do anything and R1 does some, but it's mainly Q1. So how do we do that? Well, remember we pointed to this resistor to find the ideal noise voltage at the output. We did that here, and we found out it was 3.6 nanovolts per square root hertz. So where's all the other noise coming from? Well, let's find out. So this busy looking graph shows us that. R6, the source resistance, which effectively is the noise coming in from the environment into the antenna. That is our 3.6. It's the blue curve. So I said that R8 and R9 were not going to produce anything, so I clicked on those, and I got this nice flat line down here at the bottom, so that proves that I was right. Of course, in a real amplifier, there'd be some inductance here in series with the path from the base to ground, and so it might not be completely correct, but it's close. What about R1? We said that that's not going to contribute a lot, but some, and that's the case. When I clicked on it, I got this line here, and it's, about 1 nanovolt per square root hertz. And if you square that and compare it to 3.6 squared, 3.6 squared is an order of magnitude bigger than that. So this is pretty negligible. But what's this one? Well, that is coming from the transistor, which we reasoned in our analysis was probably what was going to happen, and indeed it does. It's even bigger than the output noise would be from the source resistance alone. So this is a major contributor. This is the dominant contributor to the total of 6 nanovolts per square root hertz. And finally, to get the noise figure, remember we do 20 log of the total output noise divided by what I'm calling the ideal noise, or the noise that would happen at the output just from the source if the amplifier was noiseless, which is 3.57, which is 3.6. So 6 over 3.6, 20 log of that, is 4.5 dB. The same as we got over here. So there's a couple of different methods. In the end, I like this one better because it gives us this extra information of where the noise is coming from, but it also doesn't assume that you're perfectly matched. So I think this is a better way to do it. Take the total and divide by that from the source alone. So that brings us to the end of what I want to talk about on simulation. And our next stop is measurements. We've analyzed our circuit so we understand where the contributors are that make the most difference in the noise figure, and maybe we could optimize the circuit. We simulated it to check ourselves, make sure that was right, but also to refine it. Now we need to find out if it actually works. So we build the sucker up and test it. And the amp I built is basically this one. It's not the one with the split inductors. So here it is, down here in the bottom center. I did bias it at 5 milliamps. Here's the 2N5179 transistor, or I think it's MMBT5179, something like that. And the bias resistors and so forth. And the LC tuned circuit is right here. There is a high Q inductor, air wound inductor, and then there's a variable capacitor so I can tune the thing. The input is over here on the left. It goes through the matching network. Here's the inductor for that. I think that's the capacitor. And then the output comes out of here and goes to this connector. So how do we measure the noise figure? Well, if you're in a commercial laboratory, RF lab, or a university with really good test equipment, you might have some big piece of test equipment that costs $150,000 that you can hook your thing up to, punch a button and say, what's the noise figure? But we're not going to do that. We want to understand what's really going on. And the first thing we have to do is know what the gain of our amplifier is. And as you may know, there are many different ways to define and to measure gain. Here I'm going to be using what's called the insertion gain measurement. I have a couple of tiny spectrum analyzers. One's the original, that's shown over here, and one is the tiny SA Ultra, which is what I'm using for the readout. I've got the original one configured as a signal generator at 88.5 megahertz. And I have no modulation on it because I just want a CW signal. And I set it to a level of minus 60 dBm. And I connected its output port here, which goes to this cable, to a little CAL board that has a through connection. So there's just a wire from here to here, and then it goes out on this cable, which goes to this tiny SA Ultra. And it reads out the power level. And the power level it reads is 69.6 dBm. That's interesting because I had this set to 60, minus 60. So either there's 9 dB of loss in the cables, or one of these things is inaccurate. This one I trust more than the original one over here. This might be a clone, I'm not even sure. But in any case, don't believe every number you read. And that's the purpose of this so-called insertion gain measurement, is to get over these inaccuracies. So in the straight through case, where I take the output of this, whatever it is, it says minus 60, but it's not. I take the output of that and I go into this guy and see what it reads. And it reads minus 69.6 dBm. Then I replace the through connection with the actual amplifier. Leave this alone, don't change it, don't change the cables, and see what the output is. And now it reads minus 49.1 dBm, which is clearly about 20 dB bigger. In fact, if you do the calculation, as it shows over here, the insertion gain is minus 49.1 dBm minus a minus 69.6 dBm, which is 20.5 dB. So that's probably a pretty accurate estimate for what the actual gain of our amplifier is. All right, so insertion gain measurement is step 1. Step 2 is actually pretty easy. In step 2, I remove the signal generator input and just terminate the input in a 50 ohm load. This is a 50 ohm amplifier, so I just terminate the input. And I hook the output to a spectrum analyzer. I'm using the tiny SA Ultra. And we look at the spectrum. And in particular, we look at the noise power. So here it is. Now remember, it's a bandpass amplifier, and so there's a hump here in the noise. And that's the amplified input noise. Now, like in all engineering and all measurements, you need to be careful. I probably should have changed the reference level from minus 20 dBm to something like minus 40. I didn't do that here because there's this signal coming in. I don't know where it's coming from, but I didn't want it to saturate the amplifier inside this guy. So probably should have moved this up a little bit, but I think this is pretty accurate. It reads out minus 101.1 dBm. So what does that mean? Well, first of all, this number would change depending on what my resolution bandwidth is that I'm using. Remember, noise is proportional to bandwidth, so you got to know what that is. So here it shows that our resolution bandwidth is 100 kilohertz. So you got to write that down. So this is our total noise at the output in that resolution bandwidth. What is the expected or ideal noise using a 50 ohm termination at the input if the amplifier was noiseless? Well, it would be minus 174 dBm plus 10 log of that 100 kilohertz plus the gain, which we previously measured. and that would be minus 103.5 dBm. The actual noise measured was at least read out as minus 101.1 dBm, and that's a difference of 2.4 dB. This is 2.4 dB higher than what we would expect for a noiseless amplifier. So that is our approximate noise figure. Remember, the noise figure is how much the amplifier is degraded from its ideal. This is the approximate noise figure. Why is it approximate? Well, one is we're, again, trusting that this tiny SA power readout is accurate, and it's probably not real super accurate. It might be off by a few dB. In addition to that, something, a nuance I haven't really talked about, the resolution bandwidth that I used here in this calculation is a little different than what's called the noise bandwidth. Type that into a search engine, noise bandwidth in radio frequency circuits or something, and it'll tell you what the difference is. It's more mathematical than I want to get into here, but to a first order, resolution bandwidth and noise bandwidth are about the same. So, assuming this tiny SA has an absolute power accuracy of about plus or minus 2 dB, this could be 0.4 dB or it could be 4.4 dB. So it's not perfectly accurate. So what can we do to do better? The answer is down here in yellow. We can use the hot-cold method for better accuracy, if we need better accuracy. This is a close enough estimate for me, for what I'm doing, but sometimes you want more accuracy, and so how do you get it? Well, here are a couple of handouts that I gave in a Microwaves and Antennas senior/grad course that I was doing. And it talks about the two methods. The first method over here on the left is pretty much what our insertion gain method was all about. And I am not going to walk through all of this, but this calculation actually takes into account the noise figure of the spectrum analyzer as well as doing the insertion gain measurements, etc. So you can look at this, freeze it if you want, and read it, but I'm going to move on here in a second. The so-called hot-cold method is on the second handout. It's also called, more often probably, the Y-factor method for reasons you'll see in the equations. If you want to know about this in detail, Hewlett-Packard put out an application note 57-1. It involves the use of what's called a calibrated noise source. Then you have your amplifier, which is your device under test, your DUT, and it's got a gain and a noise factor or noise figure. And then you have your spectrum analyzer, probably with a preamp on, and it has its own noise figure. So these equations allow you to get a good estimate for what F1 is, which is what you're really looking for. So first step is to measure the gain of your amp using the insertion gain method and estimate the noise figure of your spectrum analyzer. I think the tiny SA has an ability to do that itself. Then you hook up this so-called noise source and turn it on, and then it is what's called hot, because remember, noise is kTb and T is temperature. And so when you turn this thing on, it produces a lot more noise, and that's equivalent to operating at a higher temperature, T. So that's why it's called hot. And then you turn it off, and it's so-called cold, or room temperature, 290 Kelvin. And you get the noise power measurements from the spectrum analyzer in each case. One is NH, hot, the other is noise cold. And then you go through this calculation. And if you want to know the reason for this, then go pull application note 57-1. But let me tell you roughly what it says. This Y-factor ratio is the noise power hot divided by the noise power cold. So if your spectrum analyzer is reading out in dBm, then you would take the difference of that and get a dB value and then back that into the non-dB domain, and that would give you the Y-factor. Then you can calculate the noise figure of these two pieces together. That's what I'm calling F12, the device under test plus the spectrum analyzer, using this formula, which is in the application note. ENR is the so-called excess noise ratio, and it'll be written on the noise source. So for example, we had a noise source that had an ENR of 15 dB. So you'd have to take that out of dB and put it into non-dB units. And for our 15 dB noise source, that ends up being 31.6. So subtract 1, you get 30.6. And then you take the Y out of dB domain if it's in it, and subtract 1, take the division, and that gives you the composite noise figure for these two pieces. Now, if the gain G1 of your low noise amp is much bigger than the noise figure of the spectrum analyzer, you probably don't have to do this next step. You can just use this as a decent estimate for your noise figure F1 of your low noise amp device under test. And for completeness, so that you can freeze the screen and read this stuff at your leisure if you want, I'll zoom in on this area. And this last bullet down here is one I often use. It's just a quick and dirty way to get a noise figure to within a dB or so of accuracy most of the time. Okay, but what about this noise source? Where do those come from? Well, you buy them. And this is the one that we had in our lab. It's a HP 346B. HP became Keysight, and so it's a Keysight 346B. And it's very accurate from 10 megahertz up to 18 gigahertz. So it is not cheap. It is $2,000 used. I'm not sure if this one's still made, but new ones of the ones that are made probably are $4,000 or $5,000 or more, depending on frequency range. So you're probably not going to have one of those. However, it occurred to me this morning that if I don't need that frequency range, I could build one using stuff I've got in my drawer. And I'll leave you with this slide. This is one way that you could do that. It would be fun to build this up and then get another one of these amplifiers and measure its noise figure. That would be kind of cool. Okay, so that does it for episode 6, basically. We've covered all these topics, the first 2 or 3 in part 1, and we've covered these here now. Of course, we plan to produce some more videos. They're not coming out real fast, but hopefully we'll get some out. And one of them is going to be on this Q-enhanced low noise amplifier. Here's a schematic of it, what I've got so far. The other thing I should note is that this is Rev 1B of the overall block diagram of the receiver that we're working toward in Radio Design 401 to really combat issues that we found in the receiver in Radio Design 101. So I think this is going to perform really well. And the way we'll know is to perform some benchmarks. So that's it for now. Thank you for watching this video. As always, I hope it's been helpful and interesting. And I will leave you in this video with a review of kind of what's in the other episodes in Radio Design 401 if you haven't seen those. Thanks again for watching, and hope to get a new video out sometime soon. All right. Thank you. Bye.